Over the last 5 years, artificial intelligence has made the leap from producing barely usable text to writing production-ready code. At the exact same time, image generation scaled up into highly complex video models that output scenes indistinguishable from reality. Looking at that software progress, it is reasonable to assume hardware is on the same trajectory. Silicon Valley startups are constantly dropping perfectly curated demonstration videos of humanoid robots folding laundry, making coffee, and navigating our living rooms. Watching these machines move, you could easily assume human mechanics, skilled construction workers, and warehouse staff are months away from being replaced by endless rows of tireless metal labor. But talk to the actual robotics researchers at places like MIT, and they will quickly tell you a different story. A general-purpose robot that can reliably replace your maid is still more than a decade away, and that is a highly optimistic estimate. This leaves us with a contradiction. Artificial intelligence conquered the digital world rapidly, yet it remains stalled when asked to pick up a mug in the physical one. To understand the bottleneck, we have to look at the mechanics of generation. A large language model works by processing and spitting out discrete text tokens one by one. When it drafts an essay, it has infinite time to compute the next word. If it gets a word wrong, the physical stakes are missing. A robot, however, relies on a Vision Language Action Model, or VLA. This model acts as the central nervous system for a mechanical body, translating camera pixels into physical movement. Rather than words, a VLA must constantly emit continuous values, like specific joint angles and motor torques. It streams these commands to dozens of hardware nodes, hundreds of times per second. There is zero margin for error here. If the model's calculation is off by a tiny fraction, gravity will punish you by slamming a $1 million machine into the floor. The digital-physical divide exists because reality enforces a strict set of rules. Physical movement requires continuous mathematical precision in real time, a standard digital text generators never had to meet. This disconnect illustrates more of X paradox, the observation that high-level reasoning requires very little computation, while basic sensory motor skills demand massive processing power. An AI can effortlessly crunch the probabilities required to defeat a grandmaster at chess, yet it struggles with tasks a 2-year-old toddler masters, like stacking a set of wooden blocks. You see this in the fine print of modern robotics. A company will boast about a 90% success rate in a dexterity demo, but in a household setting, that means a robot is shattering your dishes every 10th time it unloads the dishwasher. The root cause of this failure rate is a data drought. Large language models got smart by ingesting the internet. For robotics, a comparable digital database of physical movement does not exist. To work around this, engineers rely on two flawed solutions. They either clone human movements by directly teleoperating the machines, or they use trial-and-error reinforcement learning inside digital simulators, hoping the physics translates at a real world. Neither method scales perfectly yet. Until researchers discover a breakthrough for gathering continuous physical data at scale, machines will remain limited by more of X paradox. The reality is that many viral humanoid robot videos are staged. They are carefully managed demonstrations designed to generate hype and support startup valuations. If you want to purchase an advanced robot today, your options are limited. You are looking at the wait-listed frontier of actual, heavy-duty hardware like Boston Dynamics Atlas or a handful of industrial units. We should recognize general-purpose robotics not as an imminent product, but as a long-term engineering project requiring decades of iteration to match human coordination. While the physical chassis of these robots often looks ready for the showroom, the software required to bridge digital logic with real-world physics remains the critical bottleneck. For the next decade, the engineering opportunity lies in bridging that gap, writing the complex code that finally teaches a machine how to navigate gravity as naturally as it navigates text.